Welcome to fourth video. Thank you very much for watching these videos. I'm very happy that you're watching it, and I hope you're having fun with it. I really enjoy teaching it here because I can talk over and over again, and I'll be happy that you can refer to the lectures all the time. I hope you enjoy it. So this session will be on using categorizing algorithms in R. So they were using our response variables in this lecture. So our response variables are categorical variables. And that is about chapter 4 of your textbook. So what you have here are a binary response variable that means it can only take two values. And you have a bunch of predictors that you want to predict that value. For instance, you want to see whether or not tomorrow's market will be better than today or not, it will improve or not. You want to classify people to default, no default. You want to classify people to A students, B students, and so on and so forth. That's the classification method. So we're going to talk about different methods for classification. One of the most famous algorithms that are there, one of the most famous models that are there is called logistic regression. So I will first focus on that. To use logistic regressions, we need to use library ISLR. One way to call libraries is called require. So we require this library. That's another way to library. Loading. Okay, so when I said ISLR, it just started loading it. So ISLR is known to it. I'm going to use one of the variables that is used in your textbook, and actually the lecture I'm going to give you is very close to your textbook. The variable that I'm going to use is called the S market. That's the data set you have in ISLR. So let's look at the summary of that. S market. And in S market you have data for 6 years from 2001 to 2005. For every day, you know whether or not the data went up or down. That means if that day the price of the share went up, it's up, and if it went down, it's down. So 602 days out of these 6 years, the price of those shares went down, and 648 days it went up. So the variables we have are the years, are the lag one. Lag one means what was the percentage change of that specific share or that specific market yesterday. So that's lag one. Lag two means what happened the day before. Lag three is what happened 3 days ago, and so on and so forth. And you have volume, which is okay, how much of that specific share has been exchanged in that day. And that is today's data. I think the direction data is coming from the today's data. So our goal is to predict, based on the variables we have, whether or not our share will go down tomorrow or up. And that's a very important thing. If we can do the prediction very well, we can become a millionaire very easily. And as you will see, it's not that easy to do that. So let's focus on this data set and look how this data is doing. So let's look at let's pair the data. So we want to look at S market data. And we want to have since we have a categorical variable, we should say, okay, we have a categorical variable. We want you to show me that categorical variable in two different colors. And that's a way to do this. Okay, color changes with the direction data. Remember, when you use a $sign, that variable of that data set is going to be used. So if you run that, I think it takes a little bit. Okay, that is the data you will see. As you can see here, the red data and black data are so convoluted that you cannot see that much out of it. So just looking at the data doesn't give you that much of an information. So it's vitally important to use some of the methods that are available to us. So let's work on logistic regression. Remember, you need the ISLR library to deal with that. So let me put the outputs in GLM fit. In order to run the logistic regression, you have to use a model that is called GLM. That's the function you need to use. Again, as always, if you're not sure what it does, just put a question mark before it, and everything about it will be shown here. So you, as linear regression lines, LM, you have formula, you have the family you're working with. That is something new. The family you're working with can be different. The family can be, for example, binomial. If you set the family to binomial, that will become logistic regression. The family can be Gaussian or normal distribution. So the family can be changed at your will. Here, the family is always binomial. So you have a data set and you have a family, and also you need to introduce what you're regressing on what. So the general concept is exactly the same as before. So let me record everything I have in a variable called GLM fit. That is the GLM, that means generalized linear model. Why does it call generalized linear model? Because if you take log of the odds, the logistic regression line will become indeed linear. So that is generalized linear model. The output is direction of the data, right? You want to predict whether it's going up or down. So our output is direction, and we want to regress it on lag 1, lag 2, lag 3, lag 4, lag 4, lag 5, and lastly, volume. We didn't use year because it wasn't necessarily going to help us, and direction was a function of today, so there's no use to use it here. The data we are going to use is S market, and the family of distribution we are going to use is binomial. So here, family tells the GLM function that you're running logistic regression line. And here the data I'm using. Be careful here. In this regression line, I haven't divided my data into two parts of training and testing. So I'm just running all the data. But later on, I will show you how to divide your data into two sets. Okay, so we run it. Let's look at the function that we have. Let's do the summary of GLM fit. Perfect. The summary shows that none of our variables are consistent, maybe because we have a lot of variables here and they are collinear with each other. But it doesn't mean we cannot use it for prediction. So let's try using it for prediction. To use it for prediction, you just define another variable which records the predictions that you have. So we say predict, and you use your model. Okay, so I just put my model here, GLM fit. And since you're using the original data, you don't need to change that data because you're using the same thing, but you have to set the type as response. That is another thing that is different in generalized linear models if you compare it to linearized models. Okay, so GLM probability will record all the outcomes of that, and that is cool. So let's look at the outcomes, and so let's look at the first 5 outcomes, or let's look at the first 10 outcomes of this GLM probability. Not GLP, GLM. You say the probability that the first observation be up is 15.7%, the second one is 48%. And as you can see, in generalized linear models, you usually want to divide it into up and down. The probabilities are not that important. You want to see whether you categorize it in up or down. So you want to categorize the ones that are more than 50% chance that will be up to the up category, and otherwise you want to categorize it as down. One way to do it is write use an if and else function, and what it does is very simple. What it does is say, okay, if else. Here you just write the condition. So your condition is that whenever GLM probabilities are more than 50%, you want it be up. So the first thing you write in if and else function is when this condition is true, it's up. When this condition is wrong, it's down. It's vitally important. That is one of the very important things, that you should fix it to the same values you get from your data. Direction in your data was in the form of down and up with capital D, and the rest was not in capital letters, and same for up. So I'm trying to replicate what my real outcomes are here, so that I can start comparing them with real data. So my predictions for up and down is redefined for GLM probability. That means whenever the probability was more than 50%, up was assigned to that. Whenever it was less than 50%, down was assigned to that. So if you get back to the first 10 predictions we have a bunch of ups and downs. Let's compare it. For example, the first observation had 50.7% chance to happen. It became up because it was more than 50%. Second observation had 48%. That's why it became down, and so on and so forth. So that's how we make sure the outcome we get from our predictions have same format as the outcomes we had in our training. The training was down and up. That's why we changed it to down and up. In your homework, you had MPG 01, which was 0 and 1. So you should have 0 and 1s here instead of up and down or anything else, because you wanted to compare it with that part. So let's see how well our predictions are. In order to do that, let's attach our data. You remember, attach was making all our variables local. So let's attach it, and let's compare that. So let's draw a table that compares what we predicted. So our predictions, GLM predict was what are predicted. What we predicted, I named it probability. So let me change it to predict. GLM predict. Okay. Okay. I think. Okay. I have to. Let's get rid of probabilities. Okay. So we just changed it to probabilities. Let me focus on that part. Okay. So we want to compare GLM probs, which are ups and downs now, versus direction. So the table we get has down and down, up and up, up and down, and so on and so forth. These are our direction data. That is our actual data. It is our prediction data. So the table shows that 145 times the actual direction was down, we predicted down. 507 times the actual direction was up, we predicted up. So that was a good thing. But here on off diagonal for 457 times, our prediction was up. In reality, it was down. And here 141 times, our prediction was up. In reality, it was down. So that was another error we made. So we want to measure our accuracy. If we want to measure the accuracy, you just want to mean the case, average the cases that your prediction was exactly the same as your direction. So GLM prob was exactly the same as direction. So 52% of time it was exactly the same. So our model predicted things 52% of time exactly correctly. If you want to find the error, that's also very easy. You can either just subtract 1 from what you get for accuracy, or you can just find the cases that they are not equal. Exclamation mark before anything means not of that thing. So not of direction. That gives you the error. So if 52.16% of time you're correct about your prediction, therefore 47.84 times you're not. The problem of dealing with this problem that way is a very vital problem, because you didn't have any test and training data. Maybe you overfitted your data. So we must be able to split our data into training and test data. And as soon as you do that, you can just run your logistic regression line on the training data and then test it on the test data, because that's the reliable test error, not the one that you had here. So here, let's divide our data into training and test data. So it's actually very easy to do that in R. So let's define training data as the cases that the year is less than 2005. Remember, our data was from 2001 to 2005. By this way, we assign indices to train for the years that are less than 2005. That means our test data, which is defined as not trained, would become any time that train is not there. That means it's only 2005, year 2005. So our training data are for year less than 2005. Our test data is for whenever train is not. You remember the exclamation mark meant not. We used it before as well. Okay, so let's run our regression line on our training data. That's vitally important to do that. To save time, I just copy paste the GLM fit we had before above. The only thing that will be changed now is that I have to define a subset of data that we are working with. And that subset is training data, right? Because we want to work on the training data. So I added this subset after the family binomial that tells R that you're only working with a subset of training data that is relevant. And that's the same for your homework. If you have MPG0, you should only work with that subset. Okay, so we run our GLM functions. Now we want to have our predictions. But this time, we want to only work with the subset of S market data that is the test data. So that's vitally important. So our predictions, so our model must have been run on training data. Here, our predictions must be run on the test data. That is very, very important. I cannot emphasize the importance of it. So let's do that. So GLM prediction. So I just want to show you what is the difference of what we had before to now. I just copy paste whatever we had before. So GLM probabilities with prediction, GLM fit for type response. The only thing that will be changed is that you should introduce the part of S market data that is test. So you're asking it to work only on the test sample. Okay. So your new data is test data. Okay. So see what I did? I said, okay, our new data is just test data. Everything else is the same. So, okay, well, what happened? Our new data is S market data on test. Oh, sorry, on test and everything else. So the index of that is test, but we want to keep all other values of that. That means for the values that has the year that are 2005, we want to keep those, and we want to keep the lag 1, lag 2, and lag 3, and so on and so forth. That's why we put the comma here. That means use all the other values and variables that assign to that test data here. Okay, so now it can do that. Oh, perfect. So like before, we want to assign the ones that have more than 50% probability as ups. So let's call it GLO probability. Okay, our predictions would be at a simple if and else function which compares whenever our probabilities is more than 50%, it assigns it as up. Otherwise, it assigns it as down. So the next thing we want to do is to compare these ups and downs with our data and direction. But one thing that is different here is that we haven't defined that subset yet. So we just want to compare our predictions with the subset of the training data that deals with that direction data, right? That's the only thing we want to do. So we should make sure the direction test, or the actual direction of data for our test data is going to be defined the same way our predictions are defined. Remember, our predictions were for year 2005. So this thing that we should compare it with should be for year 2005 also. So that's why we redefine the direction test. That would be from the test market data and from the direction part of it. We are only interested in those that are related to test data. Okay, so our direction test would be part of the direction data that is on index test. Okay, so now you want to see how well you're doing in your confusion table. So you just write your tables, and you have some predictions versus some directions. So let's look up these. So here you have, in your test data, 77 times you had down, you predicted down, it was actually down. 44 times you predicted up, it was actually up. 97 times it's screwed because you predicted down, it actually happened to be up. And 34 times you predicted up and down. So let's see how well we did. That means how accurate we are. So we need, as always, we need to just use the mean as before. So we want to find how many times, or on average, how many times our predictions is equal to what our test or actual direction in our test data is. That is 48%. That means if you flip a coin, you would do better. So your error rate would be the times that it's not equal to that. And that is 52%. So your error is 52%. So we stop the video here. We're going to be becoming long, and in part 2 I'm going to talk about LDA and QDA, linear discriminant analysis, quadratic discriminant analysis case. And as you will see there, everything will be perfect. Now I think in that lecture I can also talk about k-nearest neighborhood. So here you learn how to deal with logistic regression. You learn how to divide your sample into the test and training data. And you understood how to use the subset of training your data and how to change your test data such that you can start working with that. So my second part would be anything that comes after that. So I assume that when you start the next one, you've already gone through this lecture. Okay, thank you very much.